Welcome to the Data Tunnel blog. In this demo, we explore the power of AI in creating accessible data dictionary descriptions using the example of the Titanic dataset from Kaggle. This instance shows how AI can facilitate the creation of accessible data dictionary descriptions more quickly. To illustrate our objective, we employ the Titanic dataset found on Kaggle. The Titanic dataset we're using contains 12 columns, featuring a blend of personal details and socio-economic data. We'll delve into our physical metadata, closely inspecting the values present in each column. In every column, 3 exemplary values have been extracted from the dataset. Personal identifiable information has been concealed, and metrics have been pinpointed for columns like survived, P-class, SIB-SP, and PARCH. The initial 2 metadata columns are the connection between the table and its columns. The Titanic acts as the overarching component encompassing around 12 subcomponents, its columns. The table row is dedicated to providing a description of the table itself. Crafting definitions for a dictionary demands significant expertise and abilities. We will guide you through the process of how generative AI can aid in this endeavor. For the first step, we'll retrieve the metadata from our dictionary. We employ toggles to input pieces of information into our finalized dictionary. This modest automation has successfully incorporated our physical metadata into the spreadsheet. In practical settings, automation would typically extract a snapshot of the data dictionary from its database source. Now, let's augment this physical metadata with the sample data needed for the personal data classification phase. Frequently, technical writers are not the real custodians of the data. The physical dictionary and its sample data alone may not suffice to precisely elucidate a column's meaning. At certain junctures, the actual data owners need to supply context. In the fourth step, we address the PI classification, which generative AI can deduce using both physical and business metadata. After determining the personal data classification, the fifth step involves combining all physical metadata into key value pairs. This compiled data, along with explicit context, is then presented to GenAI for inferencing. The sixth step assumes completion of previous stages, initiating the drafting of the initial version. This stage is time-critical and might unfold without full context, thus requiring further examination and enhancement by human reviewers. The moment we gather all necessary inputs, along with any previously missing explicit context, marks when we proceed with our final drafts. These drafts will convert physical component names into more natural terms and customize descriptions according to the format, style, and tone preferences of final consumers and/or owners. In the final step, Step 8, we take the results from Step 7 and isolate the most significant contextual attribute from the first sentence. This process is vital in information modeling to link various datasets. Prior to executing this GenAI example, we present a word count column to tally words generated by GenAI. This is done to later assess GenAI's productivity and reorient human task focus accordingly. Here, we'll demonstrate how GPT-4 manages all remaining tasks. However, as previously stated, knowledge and context are crucial, particularly since GenAI might interpret physical metadata uniquely. Aligning AI-generated data dictionary descriptions with explicit context for most metadata records is essential. Therefore, we'll activate the explicit context. When submitting queries to the OpenAI API, we'll include prompt instructions encompassing both physical metadata and explicit context for GPT-4 processing. In the Titanic dataset, explicit context is provided where physical metadata is insufficient. In some cases, a pre-trained large language model might possess sufficient knowledge to generate a preliminary description. In our example here, there are physical names like PARCH or SIB-SP where the AI may have a challenging time to return an accurate natural name. On such occasions, a human reviewer shall feed the metadata record with explicit context. We're set to initiate our first request to GPT-4 and obtain the personal data classification result. We'll input prompt instructions and physical metadata, and shortly afterward, we'll have the PI classification for our 12 columns. It's notable that GPT-4 discerns PII for the name, sex, and age columns from our provided inputs. This accuracy is due to the inclusion of physical metadata and explicit context, particularly for the age column. For each metadata record, we are now able to amalgamate all our physical data, inclusive of PI classification, into key and value pairs. These pairs are prepared as input for future requests to the OpenAI API. For the Titanic table metadata record, we'll submit only the component name and type to GPT-4. This is because the instructions for generating a table definition don't need as much physical metadata as column descriptions do. The table metadata will incorporate insights from the column metadata descriptions. We're now at step 6, initiating a request to GPT-4 for a first draft. The current prompt instructions don't yet take consumer requirements into account. This stage might precede complete input reception from owners or consumers, indicating a potential gap before step 7 when format and styling preferences are expected. GPT-4 begins by generating initial outputs for all column records using specific prompts and the available physical metadata and any explicit context. After all column descriptions are generated, the row representing the Titanic table metadata utilizes these column descriptions, combined with specific table prompts, to create an initial table-level definition. The AI creates the age columns description using both sample values and explicit context, demonstrating its capability to integrate multiple data sources. The SIB-SP columns description is another case where explicit context is integrated. Further refinement is possible by tailoring prompt instructions to meet specific formatting and styling needs, potentially leading to more natural column names. Moving to step 8, we generate these customized descriptions. Like the physical descriptions, GPT-4 provides column definitions. Once OpenAI delivers these tailored descriptions, we re-engage our GenAI assistant to extract natural names. The word count column displays the total number of words generated by GenAI in the drafts. The table metadata record compiles outputs from all column definitions. Once these definitions are complete, a final request is made to OpenAI, resulting in a tailored description for the Titanic table. This final description is crafted to match the preferred style of the data dictionary's consumers. Comparing the physical and tailored definitions highlights the final draft's adoption of a more formal and natural style, with all physical names translated into user-friendly terms. Reflecting on the column definitions, a tailored approach in definitions notably replaces physical names with natural ones, enhancing the overall clarity and accessibility of the information. The parch metadata column is another instance where explicit context is utilized, enabling Gen AI to deliver a tailored definition as expected. For the SIB-SP column, a small amount of explicit context is provided, effectively linking a natural name to its physical counterpart. Large language models excel in identifying entities or contextual attributes. Extracting natural names is a relatively simple task for Gen AI, facilitated by prompt instructions focusing on the first sentence to find and return the natural name correlating with the physical name. Evaluating productivity metrics, GPT-4 rapidly generates tailored final draft definitions with about 656 words in just a few minutes. In contrast, a human technical writer might produce 500 to 1,500 words per day, depending on knowledge and complexity, while Gen AI could potentially generate up to 40,000 words daily. We employ 3 column-level prompts and 2 table-level prompts, including one for natural name extraction, resulting in 13 physical descriptions, 13 tailored descriptions, and 13 natural names. This is our approach for conducting PI classification, sent to GPT-4 via an API call through our Excel Labs tool. We utilize specific prompts to generate physical column descriptions. A separate set of prompts is used for creating tailored column descriptions. At the table level, we apply specific prompts for both physical and tailored descriptions to create our final drafts. For extracting natural names, a basic prompt instruction is used, focusing on identifying and isolating these names. AI significantly accelerates the publishing process, enabling the creation of comprehensive final drafts for human review. However, complex topics in various fields may still require extensive drafting, with many professionals increasingly relying on AI for the bulk of this work. This shift reduces the load on technical writers, moving their focus more towards reviewing and refining AI-generated drafts. Business and scientific data dictionaries may adopt different writing styles, achievable through a range of prompt instructions. To expedite the publishing process, embracing the full potential of AI is advisable. Thank you for tuning into Data Tunnel and joining us on this journey exploring the power of AI in creating accessible data dictionary descriptions. We hope you found this discussion insightful and inspiring. Stay tuned for more exciting topics and innovations in the world of data.